There are three main goals for experiment number 6, and those goals are learning to prepare a burette for use with a titration, actually titrating using a burette, and detecting an endpoint for a titration. And we'll be doing this in the context of standardizing the concentration of an unknown base against a known primary standard, in this case potassium hydrogen phthalate. The safety concerns and precautions for this experiment are very similar to ones that we've seen before. The first and most common one is we'll be using glassware, and you need to take the standard glassware precautions, checking for chips and cracks and that kind of thing. We'll also be working with approximately 0.1 molar sodium hydroxide. And sodium hydroxide is corrosive, although at this low concentration that risk is minimized. But if you do manage to spill any sodium hydroxide solution on you, you can treat that by washing your hands or rinsing your eyes if you manage to spill some in your eyes. It's also mildly toxic, so in addition to the corrosion, the toxicity means that you should try to avoid ingesting it. The phenolphthalein solution that we'll be using as our chemical indicator is flammable because the phenolphthalein is diluted in ethanol, so avoid open flames. The phenolphthalein solution is also a mild irritant for the skin and eyes, so avoid contact. And the phenolphthalein may be carcinogenic and teratogenic. So make sure to wash thoroughly if you make contact with that chemical. The risk in this case is minimized because we'll be working with approximately 1% solutions, and that's a fairly low concentration. The final chemical that we'll be working with is potassium hydrogen phthalate, or KHP as it's more often known. It's an acid, so it's somewhat corrosive, and its primary risk is that it is an eye or skin irritant. So if you make contact with that material, make sure to wash thoroughly. In this experiment, we'll need to weigh and record exactly approximately 0.5 grams of potassium biphthalate, or KHP, into a dry 125 ml Erlenmeyer flask. And you can do this by weighing directly into the flask. You'll then need to add roughly 25 milliliters of distilled water. Do this very approximately because the volume doesn't make a huge difference. Add the water and then swirl until all of the solid dissolves. And then you're going to add 3 drops of the phenolphthalein indicator using a dropper bottle. If you add 2 or you add 4, it's not a big deal. You just don't want to add far too little or far too much. And once you've done this, you'll need to prepare a 50 milliliter burette and fill it with the unstandardized sodium hydroxide solution. For instructions on how to rinse and prepare a burette, please watch the video on preparing volumetric glassware for use. For a refresher on how to actually use the burette, please watch the video related to using a burette. When you have your sodium hydroxide in the burette, you're ready to begin titrating. So you need to take an initial volume reading from your burette and then begin adding sodium hydroxide while swirling the Erlenmeyer flask. As you do so, you should see the color start to change from clear and colorless to a faint pink color. As you add more and more sodium hydroxide, the pink color will expand to cover a larger area inside the flask. Once the pink color takes up an area about the size of a loonie or a toonie, you should really slow down the rate of addition of your sodium hydroxide and begin adding that solution very slowly. Again, continuously swirling the Erlenmeyer flask. As the pink color begins to expand more and more, you should slow down the rate of addition even further until you're adding 1 drop at a time while swirling. And as you get closer and closer to that pink color covering the entire volume of the Erlenmeyer flask, you should slow down to the point where you're adding a single drop, swirling the flask, and waiting. If you see the pink color remain, the titration is finished. If the pink color fades within 10 seconds or so, you should add a single additional drop of sodium hydroxide and swirl. And you continue this process until you've completed the titration. You know the titration is finished when you can just barely see a faint pink color that entirely fills the Erlenmeyer flask. At this point in your titration, you should stop and take a final burette reading. The difference between this final volume and the initial volume is the amount of sodium hydroxide that you've added into the Erlenmeyer flask. If you add too much sodium hydroxide, the color will look dark pink or even magenta. If you see this, you've gone too far. You've added too much sodium hydroxide. And once you've done this, you can dispose of the waste solution and determine the molarity of the sodium hydroxide solution that was used in the titration. And then repeat all of the previous steps with a new sample of KHP. And then keep repeating this until you've done at least 2 trials where the calculated molarity of the sodium hydroxide agrees within 0.002 molar. In order to find the unknown concentration of your sodium hydroxide solution, you'll have to do some pretty standard titration stoichiometry. You'll need to balance the equation for the reaction of KHP and sodium hydroxide. And this is a 1-to-1 mole ratio type of reaction. There's 1 acidic hydrogen on the KHP, and there's 1 hydroxide ion in the sodium hydroxide. Then you'll need to find the moles of KHP, which you can do because it's a primary standard, and you have the mass and the molar mass. You'll need to find the moles of sodium hydroxide with some stoichiometry. Remember that in a titration, you effectively have a limiting reagent calculation where both of the reactants are limiting. You stop at exactly the right point to use up all of both of the reactants. If you know the moles of one of them, the KHP, the stoichiometry will allow you to determine the number of moles of the other reactant, in this case, the sodium hydroxide. The end goal is to find the molarity of sodium hydroxide. You'll have found the moles by this point. Now you'll need the volume of sodium hydroxide that was used. To do this, you take the difference between the final burette reading and the initial burette reading to find the delta V, the volume that was actually added into the Erlenmeyer flask. You then know the volume and the number of moles, so you should be able to calculate the molarity of the sodium hydroxide. And then you do this for each of your trials and find the average molarity of sodium hydroxide.